Hello and welcome. Today we're going to pull back the curtain on electricity, that invisible force that, let's face it, runs our entire world. We're going to break it all down into three simple fundamentals: current, voltage, and resistance.
I mean, we use it every single second. But have you ever stopped to think about what's actually going on inside that wire when you flip a switch? It's a fantastic question, and the answer is actually way more intuitive than you might think.
You know, the easiest way to get your head around electricity is to just picture water flowing through a pipe. Seriously. We're going to use this one simple analogy, flow, pressure, and friction, to understand the three big ideas that make everything work. Okay, first up, let's talk about the flow. In our water system, this is just the water moving through the pipe, right? Well, in electricity, that flow has a name. We call it current. So electric current is simply the ordered flow of electric charge. Just like we might measure water flow in gallons per minute, we measure electric current in something called amps, or just amps for short. It's named after the brilliant French scientist André-Marie Ampère. Now, let's talk about the scale here because it's mind-boggling. This charge is carried by tiny, tiny particles called electrons. The charge on a single electron is so small that one standard unit of charge, which is called a coulomb, is made up of nearly 6 quintillion electrons. That is a 6 with 18 zeros after it, just an unbelievable number of them. All right, here's a little historical quirk that trips a lot of people up. Way back in the day, before we even knew electrons existed, scientists just assumed that current flowed from the positive end of a battery to the negative end. We call that conventional current. Now we know it's actually the negatively charged electrons flowing the other way. So while circuit diagrams still use the old convention, it's really helpful to know what's physically happening inside that wire. Okay, so we have a flow, we have a current, but what makes it flow in the first place? Water isn't just going to move through a flat pipe on its own, right? It needs some pressure. In electricity, that push is called voltage. Yep, that electric pressure is called voltage, or if you want to be a bit more formal, potential difference. A battery is basically just an electron pump. The chemical reactions inside it create this pressure, pushing the electrons to get a move on. And we measure this push in volts, named after the Italian physicist Alessandro Volta. Here's the most important thing to get about voltage. It's a measure of energy potential. 1 single volt is the amount of energy it takes to do 1 joule of work on 1 coulomb of charge. Put simply, it's the amount of oomph behind the flow. So we've got our flow, the current, and we've got our pressure, the voltage. But the journey for these electrons is never perfectly smooth. Just like a narrow or rough pipe creates friction for water, wires create an obstacle for the current, and we call this obstacle resistance. Resistance is just a material's natural tendency to get in the way of that electric flow. And it happens for a simple reason. The electrons that are trying to move are constantly bumping and colliding with the atoms of the wire itself. We measure this opposition in ohms, named after George Simon Ohm. And all of this brings us to probably the most fundamental, the most important equation in all of electronics, Ohm's law. It's so elegant because it perfectly connects our three big ideas: voltage, the push, equals current, the flow, multiplied by resistance, the obstacle. V equals I times R. This simple golden rule governs pretty much everything. So what actually determines how much resistance a wire has? Well, it boils down to 4 key things. First, length. A longer wire has more resistance, just like a longer pipe has more friction. Second, area. A thicker wire has less resistance, just like a wider pipe lets more water through. And of course, the actual material the wire's made of and its temperature play a huge, huge role. And that choice of material is absolutely everything. Some materials, like copper, have super low resistance, which makes them fantastic conductors, perfect for wiring. Other materials, like rubber, have incredibly high resistance, making them perfect insulators to keep us safe. And then you have these cool special alloys like nichrome. They have high resistance, but they don't burn up easily, which makes them ideal for the heating elements in your toaster. Speaking of special materials, get a load of tungsten. Its melting point is a jaw-dropping 3,380 degrees Celsius. This incredible ability to get white hot without actually melting is exactly why it was the go-to material for the glowing filaments in old-school incandescent light bulbs. Okay, so we have our basic ingredients: the push, the flow, and the obstacle. Now, how do we actually wire them together? Well, it turns out there are 2 fundamental ways to build a circuit. In a series circuit, everything is connected along one single path. The big downside? If one component breaks, the whole thing goes down. Think of those old, cheap holiday lights. But in a parallel circuit, the current gets multiple paths or branches to flow through, and the key advantage here is that each component works independently of the others. And this isn't some abstract theory, this is happening in your home right now. Your house is wired in parallel, and that is the crucial reason why you can turn off your toaster without the kitchen lights going dark. Every single outlet and light fixture is on its own separate, independent branch of the main circuit. So we've gone through all this trouble. Why? What's the point of pushing all these electrons through all these obstacles? Well, the payoff is usable energy, which we experience as power and, very often, as heat. Remember that resistance we talked about? It's not always a bug. Sometimes it's a feature. When current flows through something with resistance, it generates heat. Joule's law here tells us exactly how much heat, and it depends on the current, the resistance, and for how long it flows. This is precisely how your hairdryer, your electric stove, and even safety fuses work. They're designed to get hot. So the rate at which we use all this electrical energy is what we call power, and the formula couldn't be simpler. Power equals voltage times current. We measure it in watts. So when you see a 100-watt light bulb, that's just a device that's consuming energy at a rate of 100 joules every single second. Now, when your electricity bill shows up, you're not getting charged for watts, you're charged for kilowatt hours. A kilowatt hour isn't a rate, it's a total amount of energy you've used. Just one of those units on your bill is equivalent to a whopping 3.6 million joules of energy. And this brings us to what might be the single most important takeaway from all of this. When you turn on a light, you don't use up or consume the electrons. They just flow through the circuit and back out again. What you are actually paying for is the energy that the power company had to generate to do the work of pushing those electrons through your devices. So, I'll leave you with a final thought to chew on. We've seen how resistance creates heat, sometimes as a byproduct and sometimes on purpose. Just look around your home right now. What's one device where you are intentionally paying for that heating effect to do a specific job for you? Thanks for tuning in to this explainer.